What if I told you that right now, there's a cosmic battle happening in space between the strongest force in the universe and matter so dense that a teaspoon of it weighs as much as Mount Everest? And here's the mind-blowing part. Sometimes matter loses. Sometimes the very atoms that make up everything you see around you simply give up. They surrender to gravity and create something so bizarre that it breaks the laws of physics as we know them. I'm talking about neutron stars, objects so impossibly dense that they make diamonds look like cotton candy. But here's what will absolutely blow your mind. These cosmic monsters, these titans of density, can actually collapse even further. They can become black holes. And when they do, they don't just disappear. They create wounds in the fabric of space and time itself. Today, we're going to explore one of the most extreme processes in the universe. The moment when the densest matter known to science meets its match against gravity. We'll discover how something that's already compressed beyond imagination can collapse even more, and what that means for everything we think we know about reality. But before we dive into this cosmic thriller, smash that like button if you're ready to have your mind completely blown. Hit subscribe, because we're about to embark on a journey that will change how you see the universe forever. And tell me in the comments, what country are you watching from, and what time is it there? I love seeing our global community come together to explore these incredible mysteries. Let's start with something that seems impossible, but is absolutely real. Imagine taking the entire mass of our sun, that's 333,000 times more massive than Earth, and crushing it down to the size of Manhattan. Not Manhattan plus the surrounding areas, just Manhattan, the island. That's a neutron star, and they're real objects spinning in space right now. Think of it like this. If you took every car on Earth and somehow compressed them into a marble, you'd still be nowhere close to the density of a neutron star. These objects are so dense that their gravity is 200 billion times stronger than Earth's. If you dropped a marshmallow from 1 meter above a neutron star's surface, it would hit the ground with the force of a hydrogen bomb. But here's where it gets really wild. Neutron stars aren't just incredibly dense, they're incredibly weird. The solid surface of a neutron star is actually made of atomic nuclei arranged in a crystal lattice. But it's a crystal that's 10 billion times denser than steel. Below that surface, the pressure becomes so intense that protons and electrons are crushed together to form neutrons, hence the name. It's like nature's ultimate recycling program, breaking down the basic building blocks of matter and rebuilding them into something entirely new. Now, you might be wondering, how do we even know these things exist? Well, in 1967, a graduate student named Jocelyn Bell Burrell was analyzing radio telescope data when she noticed something strange. There was a signal that pulsed with incredible regularity, once every 1.3 seconds, like a cosmic lighthouse. At first, they jokingly called it LGM1 for Little Green Men. Because the signal was so regular, they thought it might be artificial. But it wasn't aliens. It was something far more incredible. It was a neutron star spinning 700 times per minute, sweeping beams of radio waves across space like a lighthouse. These objects, which we now call pulsars, gave us our first concrete evidence that neutron stars actually exist. Bell Burrell had discovered some of the most extreme objects in the universe, though tragically, she was overlooked when the Nobel Prize was awarded for this discovery in 1974. Here's what's mind-bending about neutron stars. They represent the absolute limit of how much matter can resist gravity using normal atomic forces. Every atom you're made of, every atom in the planet beneath your feet, every atom in the stars above, they're all held together by electromagnetic forces between electrons and protons. But in a neutron star, gravity is so strong that it overpowers these forces completely. It's like gravity looked at the fundamental forces of physics and said, "Not today." But wait, if gravity is powerful enough to crush atoms themselves, why do neutron stars exist at all? Why don't they just keep collapsing forever? The answer lies in something called neutron degeneracy pressure. Think of it like this. Neutrons are incredibly antisocial particles. They really, really don't like being squeezed together. When you try to pack them too tightly, they push back with a force that can resist even the incredible gravity of a neutron star. This creates a cosmic standoff, gravity pulling everything inward with tremendous force, and neutron degeneracy pressure pushing back with equal determination. For most neutron stars, this results in a stable equilibrium. They sit there in space, spinning madly and pulsing with radio waves, locked in an eternal battle between collapse and resistance. But here's the question that's going to drive our entire journey today. What happens when gravity wins? What happens when even neutron degeneracy pressure isn't enough? Because there is a limit, a precise point where gravity becomes so strong that nothing, absolutely nothing, can resist it anymore. What if I told you that there's a specific number written into the very fabric of the universe? A cosmic speed limit, but for mass instead of velocity. This number determines the fate of every star, including whether a neutron star can resist gravity's final assault or must surrender and become a black hole. And the most incredible part, we've known this number since 1930, calculated by a 20-year-old student on a ship to England. His name was Subramanian Chandrasekhar, and he was about to discover one of the most profound limits in physics. While sailing from India to Cambridge University, Chandrasekhar was working on a seemingly simple question. How massive can a white dwarf star be? White dwarfs are the collapsed cores of dead stars, incredibly dense, but not nearly as dense as neutron stars. As he worked through the mathematics during that long sea voyage, Chandrasekhar discovered something that would revolutionize our understanding of stellar death. He found that there's a maximum mass, approximately 1.4 times the mass of our Sun, beyond which electron degeneracy pressure simply cannot support a white dwarf. Above this limit, known as the Chandrasekhar limit, gravity wins decisively. The star must either shed mass or collapse further. This was revolutionary because it meant that the universe had built-in limits, hard stops where the laws of physics drew a line in the sand. But here's where the story gets really interesting for our neutron stars. Just as white dwarfs have the Chandrasekhar limit, neutron stars have their own version, called the Tolman-Oppenheimer-Volkoff limit, or TOV limit for short. This limit, calculated by Richard Tolman, Robert Oppenheimer, and George Volkoff in 1939, represents the maximum mass a neutron star can have before neutron degeneracy pressure fails. Think of it like a cosmic game of Jenga. In a regular game of Jenga, you can remove so many blocks before the tower becomes unstable and collapses. The TOV limit is like the universe's version of that critical point. You can add mass to a neutron star up to a certain point, but add just a little bit more, and the whole structure gives way catastrophically. The exact value of the TOV limit is still debated by physicists because it depends on something we don't fully understand, the equation of state of nuclear matter at extreme densities. Current estimates place it somewhere between 2.0 and 2.3 solar masses. That might not sound like much of a difference, but in cosmic terms, it's the difference between stability and complete gravitational collapse. Here's what will blow your mind about this limit. It's not just a theoretical curiosity. We've actually observed neutron stars that are dancing right on the edge of this cosmic precipice. In 2019, astronomers discovered a neutron star called J0740+6620 with a mass of 2.14 solar masses, frighteningly close to theoretical predictions for the TOV limit. This neutron star is basically playing cosmic Russian roulette, balanced on a knife's edge between existence and oblivion. But the TOV limit raises a fascinating question. What exactly happens when a neutron star exceeds this mass? Does it collapse instantly? Or is there some intermediate stage? And here's where modern physics gets really weird. Some theories suggest there might be even more exotic forms of matter that can resist gravity beyond the neutron star phase. Scientists have proposed the existence of quark stars, objects where the neutrons themselves are broken down into their constituent quarks under extreme pressure. Think of it like breaking down Lego blocks into individual plastic molecules. These hypothetical objects would be even denser than neutron stars, potentially allowing matter to resist gravity at even higher masses. There's also the theoretical possibility of strange matter, a form of matter so exotic that it might be more stable than ordinary atomic matter. If strange matter exists, it could potentially support even more massive compact objects. It's like discovering that there might be materials stronger than whatever you thought was the strongest material in the universe. But here's the crucial point that's going to drive everything we discuss next. Regardless of these exotic possibilities, there is definitely an ultimate limit. Einstein's theory of general relativity is absolutely clear on this point. There exists a mass above which no known or theoretical form of matter can resist gravitational collapse. When a neutron star reaches this point, something extraordinary and terrifying happens. The star doesn't just collapse. It creates what physicists call an event horizon, a boundary in spacetime beyond which nothing, not even light, can escape. The neutron star transforms into a black hole, and in doing so, it fundamentally changes the nature of space and time around it. But the process of this transformation is far more complex and mind-bending than you might imagine. Here's what will absolutely blow your mind. When a neutron star finally surrenders to gravity and begins its collapse into a black hole, the process happens faster than you can blink. Yet from certain perspectives, it takes forever. This isn't science fiction. This is what Einstein's equations tell us happens when matter encounters the ultimate gravitational limit. Let me paint you a picture of cosmic destruction that's both instantaneous and eternal. Imagine you're somehow able to observe a neutron star as it crosses the TOV limit. Maybe it's accreting matter from a companion star, or maybe two neutron stars have just merged. The moment the total mass exceeds that critical threshold, the neutron degeneracy pressure that has been holding the star together for potentially billions of years simply gives up. Think of it like this. Imagine you're holding up a massive weight with your arms, and you've been doing it for so long that your muscles are perfectly adapted to the load. Suddenly, someone adds just one more pound, a seemingly tiny increase, but it's enough to make your muscles fail catastrophically. That's what happens to neutron degeneracy pressure at the TOV limit. One moment it's supporting unimaginable gravitational force. The next moment it's completely overwhelmed. But here's where physics gets absolutely wild. As the neutron star begins to collapse, something extraordinary happens to time itself. According to Einstein's general relativity, time passes slower in stronger gravitational fields, an effect called gravitational time dilation. As the collapsing neutron star's gravity intensifies, time begins to slow down dramatically near its surface. This creates one of the most mind-bending scenarios in physics. If you were somehow able to watch the collapse from a safe distance, you would see the neutron star's surface falling inward. But as it approaches what will become the event horizon, the collapse would appear to slow down. The surface would become redder and redder as light climbing out of the increasingly strong gravitational field loses energy, and eventually it would appear to freeze just at the moment of black hole formation. From your distant perspective, the neutron star would appear to stop collapsing just at the critical moment, its surface frozen in time at the event horizon. But this is just an illusion created by extreme gravitational time dilation. From the perspective of the matter actually doing the collapsing, the process continues relentlessly. Here's the truly mind-blowing part. If you were somehow riding along with the collapsing matter, which, thankfully, you're not because you'd be instantly vaporized, you would experience the collapse differently. From your perspective, falling with the matter, there would be no moment where time slows down or stops. You would pass through what becomes the event horizon in a finite amount of your personal time. This creates what physicists call the frozen star versus black hole paradox. From the outside universe's perspective, the neutron star never quite becomes a black hole. It just freezes at the moment of collapse forever. But from the perspective of the collapsing matter, and from the perspective of the physics happening locally, a black hole definitely forms. Both perspectives are equally valid, which tells us something profound about the nature of reality itself. Your perspective literally determines what you observe to be true. But the weirdness doesn't stop there. As the neutron star's core collapses past the event horizon, it doesn't stop. It continues falling toward what general relativity predicts is a point of infinite density called a singularity. This is where our current physics literally breaks down. At the singularity, the curvature of spacetime becomes infinite, density becomes infinite, and the laws of physics as we know them simply stop working. Think of it like trying to divide by zero on a calculator. The mathematics just can't handle it. That's what happens to our equations when we try to describe what happens at the center of a newly formed black hole. We know something is there, but our current theories are completely inadequate to describe it. Recent research by scientists like Abhay Ashtekar at Penn State University suggests that quantum effects might prevent the formation of true singularities, instead creating what they call a quantum bounce that could potentially lead to the birth of a new universe. But these theories are still highly speculative and require physics beyond our current understanding. What we do know for certain is that once the event horizon forms, the collapsed neutron star has fundamentally changed the structure of spacetime around it. It's no longer just a very dense object. It's become a region where space and time themselves are so severely curved that they form a kind of one-way membrane around the collapsed matter. And here's something that will blow your mind. The event horizon isn't the physical surface. If you could somehow survive crossing it, you wouldn't feel anything special happen at that moment. The event horizon is more like a point of no return defined by the geometry of spacetime itself. It's the boundary where the escape velocity equals the speed of light. And since nothing can travel faster than light, nothing can escape from within this boundary. What if I told you that the moment a neutron star transforms into a black hole, it doesn't just disappear quietly into the cosmic night. Instead, it announces its birth with some of the most violent and energetic events in the entire universe. Explosions so powerful they can be seen from billions of light years away and can briefly outshine entire galaxies, containing hundreds of billions of stars. We're talking about gamma-ray bursts, short-period bursts that release more energy in seconds than our sun will produce in its entire 10 billion-year lifetime. And here's the mind-blowing connection. Many of these cosmic fireworks shows are actually the birth cries of new black holes, created when neutron stars finally succumb to gravity's relentless pull. Let me tell you about one of the most incredible astronomical discoveries of the 21st century. On August 17, 2017, gravitational wave detectors, LIGO and Virgo, detected something extraordinary: the collision and merger of two neutron stars located 130 million light-years away. This event, designated GW170817, was like nothing scientists had ever observed before. For the first time in history, we didn't just detect gravitational waves from such an event. We also saw it happen with traditional telescopes. The detection was made possible by the pioneering work of scientists like Kip Thorne, Rainer Weiss, and Barry Barish, who won the 2017 Nobel Prize in Physics for their development of the LIGO Gravitational Wave Observatory. Their work opened up an entirely new window into the universe, allowing us to literally feel the vibrations in spacetime caused by cosmic catastrophes. But here's what makes GW170817 particularly relevant to our story. Astronomers aren't entirely sure what happened to the merged object. The combined mass of the two neutron stars was approximately 2.7 solar masses, well above the TOV limit for a single neutron star. This means the merger definitely created something, But the question is, what? Think of it like this. Imagine you have two overpacked suitcases that are right at the weight limit for airline travel. Individually, they're fine. But if you somehow combine their contents into a single suitcase, it would be way over the limit and wouldn't be allowed on the plane. That's essentially what happened when these two neutron stars merged. The result was definitely over the weight limit for neutron star stability. The most likely scenario is that the merger created a black hole, but possibly not immediately. Some theoretical models suggest that the merged object might have briefly existed as a hypermassive neutron star, an object supported temporarily by rapid rotation and magnetic fields, but ultimately doomed to collapse once these stabilizing effects diminished. This raises a fascinating question. How long does it take for a neutron star to actually become a black hole once it exceeds the mass limit? The answer depends on several factors, including how rapidly the object is rotating and the strength of its magnetic field. A rapidly spinning neutron star can actually support more mass than a non-rotating one, thanks to the centrifugal force counteracting gravity. But here's the incredible part. Even if rotation and magnetic fields can temporarily prevent collapse, they're fighting a losing battle. Rotating neutron stars gradually slow down over time due to energy loss through electromagnetic radiation. As they spin down, their ability to support extra mass decreases. Eventually, gravity always wins. When the final collapse does occur, it can trigger some of the most spectacular explosions in the universe. The process can generate enormous magnetic fields, quadrillions of times stronger than Earth's magnetic field, that can accelerate particles to nearly the speed of light and create focused beams of gamma radiation. These beams, if they happen to point toward Earth, appear to us as gamma ray bursts. But there's another type of neutron star collapse that's even more dramatic, the core collapse supernova. When a massive star, at least 25 times more massive than our Sun, reaches the end of its life, its core can collapse directly into a black hole. This process bypasses the neutron star phase entirely and can trigger what's called a hypernova or collapser. These events are so energetic, they can create long-duration gamma-ray bursts that last for minutes or even hours. The collapsing stellar core forms a black hole, but the infalling material doesn't stop there. It continues to spiral inward, forming an accretion disk that glows white-hot and launches jets of material at nearly the speed of light. Here's something that will absolutely blow your mind. When we observe these gamma-ray bursts from neutron star mergers or stellar collapses, we're not just seeing the death of stars, we're witnessing the creation of some of the universe's most extreme objects. Each gamma-ray burst represents the birth of a new black hole, a new region where space and time are so severely warped that they form a permanent scar in the fabric of reality itself. But the story doesn't end with the black hole's formation. Once created, these cosmic monsters begin to influence their surroundings in ways that can reshape entire galaxies. They can continue to grow by accreting matter from their surroundings, and under certain conditions, they can launch jets of material that extend for hundreds of thousands of light years, affecting star formation across vast regions of space. The transformation of a neutron star into a black hole represents one of the most extreme phase transitions possible in the universe. The moment when matter gives up its fight against gravity and surrenders to the curvature of spacetime itself. Here's what will blow your mind. Not all neutron stars that become black holes do so in spectacular explosions. Some take the slow route, gradually stealing mass from a companion star over millions or billions of years, like cosmic vampires slowly draining their victims until they cross the point of no return. And this process reveals something profound about how gravity can be both patient and inevitable. Picture this scenario. You have a neutron star in a binary system with a normal star, maybe something like our Sun. The two objects orbit each other in a cosmic dance that can last for billions of years. But here's where it gets interesting. If the neutron star and its companion are close enough together, the neutron star's incredibly strong gravity can start pulling material off the surface of the normal star. Think of it like this. Imagine you're stirring a pot of thick soup with a spoon that has incredibly strong magnetism. As you stir, the spoon gradually pulls bits of the soup toward it, creating streams and spirals of material. That's essentially what happens in these binary systems. The neutron star's gravity creates streams of material that spiral inward, forming what astronomers call an accretion disk. This process was first understood through the groundbreaking work of Yakov Zeldovich and Igor Novikov in the Soviet Union during the 1960s. Realized that when material falls toward an extremely compact object, it doesn't just fall straight in. Conservation of angular momentum forces it to spiral inward, heating up to incredible temperatures and glowing brilliantly in X-rays. But here's the crucial point for our story. Every bit of material that the neutron star accretes adds to its total mass. And remember, neutron stars have that hard limit, the TOV limit, beyond which they cannot remain stable. So every gram of stolen material brings the neutron star one step closer to gravitational collapse and black hole formation. The beautiful and terrifying thing about this process is its inexorable nature. Each particle of accreted hydrogen, each atom stolen from the companion star, is like a single grain of sand added to a cosmic scale. Individually, these additions seem insignificant, but collectively, they're pushing the neutron star toward a threshold beyond which there's no return. What makes this even more fascinating is that we can actually observe this process happening in real time. Well, cosmic real time, which means over periods of years and decades rather than seconds. X-ray binary systems, where neutron stars are actively accreting material from companion stars, are some of the brightest X-ray sources in our galaxy. One of the most famous examples is Cygnus X1, though that's actually a black hole system. But there are numerous neutron star X-ray binaries where we can watch this cosmic feeding process in action. Systems like Scorpius X1 and Hercules X1 show us neutron stars that are steadily gaining mass through accretion. Here's something that will absolutely blow your mind. The accretion process itself can sometimes be self-limiting. When material falls onto the surface of a neutron star, it can trigger nuclear fusion reactions that release enormous amounts of energy. These are called X-ray bursts, and they can be so powerful that they temporarily blow away the incoming material, like a cosmic sneeze that clears the neutron star's immediate surroundings. But even with these periodic outbursts, the long-term trend is still mass gain. And here's where the story gets really interesting. Theoretical calculations suggest that a neutron star needs to accrete only about 0.1 to 0.2 solar masses, roughly the mass of Jupiter, to push it over the TOV limit and trigger collapse into a black hole. That might seem like a lot of material, but in cosmic terms, it's actually quite modest. A Sun-like star contains about 1,000 Jupiter masses, so a neutron star only needs to steal about 0.01% of its companion's mass to reach the critical threshold. At typical accretion rates, this process can take anywhere from 100 million to 1 billion years. A long time by human standards, but a blink of an eye in cosmic history. There's another pathway that's even more dramatic, the accretion-induced collapse of white dwarf stars. While this doesn't directly involve neutron stars, it shows us another way that gradual mass accumulation can trigger sudden gravitational collapse. When a white dwarf in a binary system accretes enough material to exceed the Chandrasekhar limit, it can either explode as a type Ia supernova or, under certain conditions, collapse directly into a neutron star or even a black hole. But here's what's truly mind-bending about accretion-driven collapse. The transition from neutron star to black hole can happen gradually in some cases, but the final moment is still catastrophically sudden. It's like filling a bathtub with water. You can add water slowly and steadily for a long time, but But when the tub finally overflows, it happens all at once. Recent computer simulations by researchers like Christian Oteet at Caltech have shown that when an accreting neutron star finally exceeds the TOV limit, the collapse to a black hole can happen in milliseconds, even though the accretion process that led to that moment might have taken millions of centuries. This raises a fascinating question. Are there neutron stars out there right now that are just a few more years or decades away from crossing this threshold? Are we potentially witnessing the final chapters in the lives of some of these cosmic monsters, not knowing that we're watching objects that are about to transform into something fundamentally different? What if I told you that the moment when a neutron star becomes a black hole can be predicted with mathematical precision? That there are equations written down decades ago by some of the greatest minds in physics that can tell us exactly when matter will surrender to gravity? And here's the mind-blowing part. These equations reveal that the universe operates according to mathematical principles so precise and universal that they apply equally to the smallest quantum particles and the largest cosmic structures. Let me introduce you to the Einstein field equations, 10 interconnected partial differential equations that describe how matter and energy curve spacetime, and how that curved spacetime tells matter how to move. These equations, first published by Albert Einstein in 1915, are arguably the most beautiful and profound mathematical expressions ever written by human beings. The equations look deceptively simple when written in their compact form. G equals 8t. But don't let the simplicity fool you. Packed into this elegant mathematical statement is a complete description of gravity, space-time, and the fundamental relationship between matter and the geometry of the universe itself. Here's what will blow your mind. When you apply these equations to the specific case of a spherically symmetric, non-rotating massive object, you get what's called the Schwarzschild solution, worked out by Karl Schwarzschild in 1916 while he was literally fighting in World War I. Tragically, Schwarzschild died of an autoimmune disease contracted at the Russian front just months after deriving this solution. But his work gave us the first mathematical description of black holes. The Schwarzschild solution reveals something extraordinary. There's a critical radius, now called the Schwarzschild radius, where the curvature of spacetime becomes so extreme that it forms an event horizon. For any spherical object, you can calculate this radius using the incredibly simple formula. Rs equals 2gm per c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. Think of it like this. Every object in the universe has a theoretical Schwarzschild radius, the size it would need to be compressed to in order to become a black hole. For Earth, that radius is about 9 millimeters, smaller than a grape. For the Sun, it's about 3 kilometers. For a typical neutron star with 1.4 solar masses, it's about 4 kilometers. But here's the crucial insight. A neutron star with a radius of about 12 kilometers is already incredibly close to its Schwarzschild radius. It's like nature has compressed matter to within a factor of 3 of the absolute limit imposed by general relativity. That's how extreme these objects are. They're already dancing on the edge of becoming black holes. Now, let's talk about the mathematics that determines when a neutron star actually crosses this threshold. The Tolman-Oppenheimer-Volkoff equations, derived in 1939, describe the hydrostatic equilibrium of a relativistic fluid sphere. Basically, they tell us how massive a neutron star can be before it collapses. These equations incorporate both general relativity and the quantum mechanics of dense nuclear matter. They're incredibly complex to solve, requiring sophisticated computer simulations and assumptions about the equation of state of matter at densities exceeding that of atomic nuclei. But here's what's remarkable. Despite all this complexity, the equations give us a definitive answer. There is a maximum mass, the TOV limit, beyond which no neutron star can exist. Current calculations, incorporating our best understanding of nuclear physics, Place this limit at approximately 2.0 to 2.3 solar masses. What makes this even more incredible is that we can test these theoretical predictions against real observations. The 2017 neutron star merger GW170817 provided unprecedented data about neutron star properties. By analyzing the gravitational waves from this event, scientists were able to constrain the neutron star equation of state and refine their estimates of the maximum mass. The LIGO-Virgo collaboration, led by scientists like Gabriela Gonzalez and David Reitz, has revolutionized our ability to probe these extreme physics regimes. Their detections of gravitational waves from neutron star mergers provide direct experimental tests of general relativity in the strong field regime conditions, where space-time curvature is so extreme that it would have been impossible to test these theories any other way. But here's something that will absolutely blow your mind. The mathematics tells us that the collapse from neutron star to black hole isn't just a smooth transition. There's actually a discontinuous jump in the properties of spacetime. One moment you have a neutron star with a defined surface that you could, in principle, stand on if you could somehow survive the crushing gravity. The next moment, you have a black hole with an event horizon, a boundary in spacetime itself beyond which no information can escape. This discontinuity reveals something profound about the nature of reality. The mathematics of general relativity tells us that there are fundamental phase transitions in the structure of spacetime itself. Just as water can undergo a phase transition from liquid to gas at a specific temperature and pressure, matter can undergo a phase transition from having a physical surface to becoming a geometric feature of spacetime. Recent work by physicists like Abhay Ashtekar and Parampreet Singh suggests that quantum effects might modify the Einstein equations at extreme densities, potentially preventing the formation of true singularities and replacing them with quantum bounces. But these theories are still highly speculative and require a complete theory of quantum gravity to fully understand. The mathematical precision of these predictions is what makes the study of neutron star collapse so remarkable. We're not just telling cosmic stories, we're making specific, testable predictions about some of the most extreme conditions in the universe using mathematics developed on Earth by human beings. Here's what will blow your mind. Astronomers are actually hunting for neutron stars in the process of collapsing into black holes right now, using some of the most sophisticated technology ever created by humanity. And they're not just looking. They're finding evidence that these cosmic transformations are happening all around us, sometimes in our own cosmic neighborhood. We're living in the golden age of gravitational astronomy, where we can literally feel the universe shaking as these catastrophic events unfold. Let me tell you about one of the most ambitious scientific projects in human history: the Laser Interferometer Gravitational Wave Observatory, or LIGO. Picture two L-shaped buildings, each with arms extending 4 kilometers in perpendicular directions. Inside these arms, laser beams bounce back and forth between mirrors, measuring distances with such incredible precision that they can detect changes smaller than 1/10,000th the width of a proton. This sounds impossible, but it's real, and it's allowing us to detect ripples in space-time itself, gravitational waves created when massive objects, like neutron stars, spiral into each other and merge. The sensitivity is so extreme that LIGO can detect gravitational waves from neutron star collisions happening billions of light years away. But here's where it gets really interesting for our story. When LIGO detects a neutron star merger, astronomers around the world immediately point their telescopes at that region of sky, searching for the electromagnetic signatures of these events. What they're looking for are the birth cries of new black holes, gamma-ray bursts, X-ray emissions, and optical flashes that might reveal the moment when neutron star matter finally surrenders to gravity. The 2017 event GW170817 was a perfect example of this multi-messenger astronomy in action. Within minutes of LIGO and Virgo detecting the gravitational waves, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same direction. This was followed by optical observations that tracked the event's afterglow for weeks, providing unprecedented insights into what happens when neutron stars merge. But here's what makes this detection particularly relevant to our question. Scientists still aren't entirely sure what the final outcome of GW1708-17 was. The total mass of the merged object was definitely above the TOV limit for a single neutron star, which means it had to become either a black hole or something even more exotic. The fact that we detected a gamma-ray burst suggests that a black hole probably did form, but the exact timing and mechanism remain subjects of intense research. Think of it like this. We witnessed a cosmic car crash in slow motion, where two incredibly dense objects smashed together with such violence that they shook the very fabric of spacetime. But the debris cloud from this crash was so thick and chaotic that we're still trying to figure out exactly what emerged from the wreckage. This uncertainty highlights one of the biggest challenges in observational astronomy. The final moments of neutron star collapse happen so quickly and in such extreme conditions that they're incredibly difficult to observe directly. We're like cosmic forensic scientists trying to reconstruct the crime scene from the evidence left behind. But astronomers have developed clever techniques to search for these events. One approach involves monitoring X-ray binary systems, neutron stars that are actively accreting material from companion stars. By measuring the X-ray emissions from these systems over time, astronomers can track whether the neutron star is gaining mass and approaching the critical threshold for collapse. Dr. Fariel Zoll at the University of Arizona has been pioneering this approach, using observations from NASA's NICER, Neutron Star Interior Composition Explorer, to measure the masses and radii of neutron stars with unprecedented precision. Her work is helping us understand exactly how close some neutron stars are to the critical mass limit. But here's something that will absolutely blow your mind. We might have already witnessed neutron stars collapsing into black holes without realizing it. Some gamma-ray bursts, those incredibly energetic flashes of gamma radiation that can briefly outshine entire galaxies, might be the death screams of neutron stars crossing the TOV limit. The connection between gamma-ray bursts and neutron star collapse was first proposed by Stan Woosley at UC Santa Cruz in the 1990s. Woosley realized that when a rapidly rotating neutron star finally collapses into a black hole, the conservation of angular momentum could create an incredibly powerful magnetic dynamo, capable of launching jets of material at nearly the speed of light. These jets, if they happen to point toward Earth, would appear as short gamma-ray bursts lasting only a few seconds, but releasing more energy than our sun will produce in its entire lifetime. It's like the universe's ultimate fireworks display, announcing the birth of each new black hole, with a cosmic light show visible across billions of light years. But detecting these events is like trying to spot a camera flash going off on the other side of the world. You have to be looking in exactly the right direction at exactly the right time. This is why gamma-ray burst astronomy relies on networks of satellites constantly scanning the entire sky, ready to alert ground-based telescopes the moment one of these cosmic beacons lights up. The Swift Gamma-Ray Burst mission, launched in 2004, has detected hundreds of these events, providing crucial data about the rate at which neutron stars might be collapsing into black holes throughout the universe. What Swift has revealed is staggering. Gamma-ray bursts are going off somewhere in the observable universe, roughly once per day. If even a fraction of these represent neutron star collapses, it means we're witnessing the birth of new black holes on a regular basis. Here's what's even more incredible. Some of these gamma-ray bursts are so energetic that they temporarily affect Earth's atmosphere from distances of thousands of light years away. The burst GRB2210099, detected in October 2022, was so powerful that it saturated detectors on multiple satellites and created measurable changes in Earth's ionosphere. This boat brightest of all time, gamma-ray burst might have been the collapse of a neutron star into a black hole happening relatively nearby in cosmic terms. But the observational hunt for neutron star collapse extends beyond just waiting for these dramatic events. Astronomers are also using gravitational wave detectors to search for more subtle signatures. When a single neutron star collapses into a black hole, it should produce a characteristic gravitational wave signature, a brief chirp as the object's quadrupole moment changes during collapse. These solo collapse events would be much harder to detect than binary mergers because they involve only one object and happen much more quickly. But future gravitational wave detectors, like the proposed Einstein telescope and Cosmic Explorer, might be sensitive enough to catch these events from across the observable universe. There's also the possibility of detecting precursor signals, gravitational waves, emitted by a neutron star in the moments or hours before it finally collapses. A neutron star that's right at the mass limit might oscillate or ring like a bell as it struggles against gravity, potentially creating detectable gravitational wave emissions before the final collapse. The hunt for these cosmic transformations represents one of the most exciting frontiers in modern astronomy. We're not just passive observers of the universe anymore. We're active detectives, using multiple types of telescopes and detectors to piece together the most extreme physical processes imaginable. What if I told you that the collapse of neutron stars into black holes isn't just some distant cosmic curiosity, but a process that's fundamentally connected to your existence, your daily life, and even the device you're using to watch this video? Here's the mind-blowing truth. The death throes of massive stars, including the formation of black holes from neutron star collapse, are directly responsible for creating and distributing the heavy elements that make complex chemistry, and therefore life, possible. Let me blow your mind with this connection. The calcium in your bones, the iron in your blood, the oxygen you breathe right now, none of these elements existed when the universe was young. They were forged in the nuclear furnaces of massive stars and explosively distributed throughout the cosmos when those stars died. But here's the part that will absolutely amaze you. Some of the heaviest elements in your body, like gold, platinum, and rare earth metals, can only be created in the most extreme nuclear processes imaginable. When neutron stars merge or collapse, they create conditions so extreme that they can forge elements that are impossible to create any other way. The collision that we detected as GW170817 probably created more gold than the mass of Earth. Hundreds of Earth masses worth of precious metals, scattered across space in a single cosmic event lasting just a few seconds. Think about this for a moment. The gold in any jewelry you might be wearing, the rare earth elements in your smartphone's electronics, the platinum in catalytic converters. These atoms were literally forged in cosmic catastrophes involving neutron stars. You are wearing and using the remnants of some of the most violent events in the universe. Your body contains stardust, but more than that, it contains the products of cosmic destruction on an unimaginable scale. But the connection goes even deeper than just the elements in your body. The process of neutron star formation and collapse plays a crucial role in regulating star formation throughout the galaxy. When massive stars explode as supernovas, events that can create neutron stars or black holes, they inject enormous amounts of energy into the interstellar medium, creating shock waves that can both trigger the formation of new stars and blow away the gas needed for star formation. This creates a cosmic feedback cycle that has been operating for billions of years, regulating the rate at which new stars form and ensuring that galaxies like our own Milky Way continue to produce new generations of stars and planets. Without this regulation, galaxies might have burned through all their gas early in cosmic history, leaving the universe cold and dark. Here's something that will change how you think about time and space. The neutron stars that exist in our galaxy today are the remnants of massive stars that died millions or billions of years ago. Some of these neutron stars are slowly accreting material and might be just centuries or millennia away from collapsing into black holes. In cosmic terms, this means that the universe around us is constantly changing, with new black holes being born and old neutron stars dying on timescales that span human civilizations. But there's an even more profound connection to consider. The gravitational waves from neutron star mergers and collapses don't just carry energy. They carry information about the most extreme physics in the universe. When LEGO detects these waves, it's not just measuring cosmic events. It's providing us with data that tests the very foundations of our understanding of space, time, and matter. This has practical implications that might affect your life in ways you never imagined. The precision timing systems that make GPS satellites work rely on our understanding of general relativity, the same theory that predicts neutron star collapse and black hole formation. The atomic clocks used in these systems are so precise that they can detect the tiny gravitational time dilation effects predicted by Einstein's equations. Without our understanding of these extreme gravitational effects, GPS would be off by several kilometers within hours. Your smartphone's ability to know where you are depends fundamentally on our understanding of the same physics that governs neutron star collapse. The cosmic and the mundane are connected in ways that would have seemed like magic to previous generations. But perhaps the most profound connection is philosophical. The study of neutron star collapse forces us to confront fundamental questions about the nature of reality itself. What happens to information when it falls into a black hole? Is the singularity at the center of a black hole a real physical object, or a sign that our current theories are incomplete? These aren't just academic questions. They're probing the deepest mysteries of existence itself. The fact that we can even ask these questions, that we can detect gravitational waves from events billions of light years away, that we can use mathematics developed by humans to predict the behavior of matter under conditions so extreme they would have been unimaginable just a century ago. This says something profound about our place in the universe. You are not separate from the cosmos. You are part of it in the most literal sense. The atoms in your body were forged in stellar furnaces in explosive cosmic events. The physics that governs neutron star collapse is the same physics that governs the chemical reactions in your brain that allow you to understand these concepts. You are the universe becoming aware of itself, using tools and mathematics to probe its own deepest mysteries. When you look up at the night sky and realize that some of those points of light might be neutron stars just years away from becoming black holes, you're not just observing distant objects. You're witnessing the ongoing evolution of the cosmos itself. And your ability to understand and appreciate these processes makes you a participant in the universe's journey of self-discovery. Here's what will absolutely blow your mind and challenge everything you think you know about reality. When a neutron star collapses into a black hole, it creates one of the most profound puzzles in modern physics, a paradox so deep that it questions the very nature of information, causality, and the fundamental structure of reality itself. This isn't just abstract theoretical physics. This is a crisis that threatens to tear apart our understanding of how the universe works at its most basic level. Let me introduce you to Stephen Hawking's most famous and disturbing discovery. In 1974, Hawking applied the principles of quantum mechanics to black holes and discovered something that shocked the physics community. Black holes aren't perfectly black. They actually emit radiation due to quantum effects near the event horizon. This radiation, now called Hawking radiation, means that black holes slowly evaporate over time, eventually disappearing completely. But here's where the paradox emerges, and it's so profound that it's been keeping physicists awake at night for nearly 50 years. According to quantum mechanics, information cannot be destroyed. This is one of the most fundamental principles of physics, known as unitarity. Every quantum process must be reversible in principle, meaning that if you could run the universe backward, you could reconstruct any previous state from complete knowledge of the current state. But when a neutron star collapses into a black hole, all the information about its internal structure, the quantum states of every particle, the exact distribution of matter, the specific nuclear configurations that made each neutron star unique, appears to disappear forever when the black hole eventually evaporates through Hawking radiation. Think of it like this. Imagine you had a book containing all of human knowledge, and you threw it into a fireplace. Classical physics would say the information is destroyed when the book burns. But quantum mechanics says that's impossible. The information must be preserved somehow in the smoke, ash, and heat produced by the fire. You might not be able to practically reconstruct the book, but the information must still exist in some form. But black holes seem to violate this principle completely. When they evaporate through Hawking radiation, the radiation appears to be completely thermal, random and featureless, containing no information about what fell into the black hole. It's as if the universe has a cosmic paper shredder that can permanently destroy information, violating one of the most sacred principles of physics. This paradox has led to some of the most radical and mind-bending proposals in theoretical physics. Some physicists, led by researchers like Juan Maldacena at the Institute for Advanced Study, propose that the information isn't actually lost. It's encoded on the black hole's event horizon in a holographic manner. According to this idea, the three-dimensional information that falls into a black hole is somehow preserved as a two-dimensional pattern on the black hole's surface. Think of it like a hologram on a credit card, a two-dimensional surface that contains three-dimensional information. The holographic principle suggests that all the information in any volume of space can be encoded on the boundary of that space. If this is true, then the event horizon of a black hole formed from neutron star collapse would contain all the information about the original neutron star, encoded in ways we don't yet understand. But other physicists have proposed even more radical solutions. Leonard Susskind at Stanford University has argued for the existence of firewalls at black hole event horizons, regions of such intense energy density that they would instantly incinerate anything attempting to cross them. This would solve the information paradox by preventing information from ever actually entering the black hole. But it would violate Einstein's equivalence principle, which says that freely falling observers shouldn't notice anything special about crossing an event horizon. Here's where it gets even more mind-bending. Some physicists propose that information falling into black holes doesn't disappear or get encoded on the event horizon. Instead, it gets scrambled and eventually re-emerges in the Hawking radiation, but in such a complex and chaotic way that it would take longer than the age of the universe to decode. This is like taking a book, cutting it up into individual letters, and then randomly redistributing those letters across billions of pages. The information is technically still there, but it's so thoroughly mixed up that recovering the original text would be practically impossible. Recent work by physicists like Ahmed Almhiri and his colleagues has revealed even deeper layers to this paradox. They've shown that if information is preserved in black holes, then the interior of a black hole must be connected to its exterior in ways that seem to violate our understanding of space and time. These connections, called Einstein-Rosen bridges or wormholes, would mean that the collapse of a neutron star creates not just a black hole, but a tunnel through space-time itself. But here's what makes this relevant to neutron star collapse specifically. When a neutron star becomes a black hole, we might be creating a permanent record of that neutron star's quantum information in the structure of space-time itself. Every neutron star that has ever collapsed might have left an indelible imprint on the fabric of reality, encoded in ways we're only beginning to understand. This raises profound questions about the nature of reality itself. If information is truly preserved in black holes, then nothing is ever really lost. Every quantum state that has ever existed continues to exist in some form, hidden behind event horizons throughout the universe. The collapse of a neutron star wouldn't be the death of that object, but rather its transformation into a different kind of existence. Some physicists even speculate that the interiors of black holes might contain entire universes, baby universes that form when the collapsing matter reaches infinite density at the singularity. If this is true, then every neutron star collapse might be giving birth to a new cosmos, complete with its own space and time. The information paradox forces us to confront the possibility that our understanding of reality is fundamentally incomplete. Either quantum mechanics is wrong, or general relativity is wrong, or the universe operates according to principles so strange and counterintuitive that we haven't even begun to imagine them yet. What if I told you that the collapse of a neutron star might not always lead to a black hole? That there could be even more exotic forms of matter lurking in the universe, states of matter so strange and counterintuitive that they challenge our understanding of what matter itself can be. Here's what will blow your mind. The extreme conditions inside collapsing neutron stars might create forms of matter that don't exist anywhere else in the universe. And some of these exotic states might be able to resist gravity in ways we never imagined possible. Let me introduce you to one of the most bizarre possibilities in physics: strange matter. This isn't science fiction. It's a legitimate theoretical possibility based on our current understanding of quantum chromodynamics, the theory that describes the strong nuclear force. Strange matter would be composed of roughly equal numbers of up, down, and strange quarks, creating a form of matter that might actually be more stable than ordinary atomic matter. Here's the mind-bending part. If strange matter is more stable than ordinary matter, then every atom in your body, every atom in the Earth, every atom in every star might be in a metastable state, stable for now, but not the lowest possible energy configuration. It would be like discovering that every building in the world is built on a foundation that could potentially collapse into a more stable configuration, releasing enormous energy in the process. The possibility of strange matter was first proposed by Edward Witten at the Institute for Advanced Study in 1984. Witten realized that at the extreme densities found in neutron star cores, quarks might not remain confined within individual neutrons and protons. Instead, they might form a quark soup where quarks move freely throughout the entire object. And if this quark soup contains strange quarks, the resulting strange matter might be absolutely stable. This leads to the possibility of strange stars, objects that look like neutron stars from the outside, but have fundamentally different internal structure. A strange star would have a thin crust of ordinary matter overlying a core of strange quark matter. From a distance, you couldn't tell the difference between a strange star and a neutron star, but the physics inside would be completely different. But here's where it gets really wild. Strange stars might be able to support more mass than neutron stars. The equation of state for strange matter, the relationship between pressure and density, might be stiffer than that of neutron matter, potentially allowing strange stars to exist at masses well above the Tove limit for neutron stars. Think of it like this. If neutron stars are like buildings made of steel, then strange stars might be like buildings made of some hypothetical supermaterial that's even stronger than steel. They could potentially support more weight before collapsing, pushing the maximum mass limit even higher. This raises a fascinating possibility. Some objects that we currently think are black holes might actually be strange stars. The distinction matters because strange stars, unlike black holes, would have actual physical surfaces that you could, in principle, land on, ignoring the fact that you'd be instantly vaporized by the intense radiation and gravity. But strange matter isn't the only exotic possibility. Recent theoretical work has explored the possibility of color superconducting phases in quark matter. At extremely high densities and relatively low temperatures, quarks might form Cooper pairs similar to the electron pairs in ordinary superconductors, creating a state of matter that conducts the strong nuclear force without resistance. These color superconducting phases could have properties even more exotic than strange matter. They might support enormous magnetic fields, exhibit frictionless flow of nuclear matter, or have other properties that we can barely imagine. The phase diagram of quantum chromodynamics at extreme densities might contain multiple exotic phases, each with different abilities to resist gravitational collapse. Dr. Krishna Rajagopal at MIT and his colleagues have spent decades exploring these possibilities, using sophisticated theoretical techniques to map out the possible phases of matter under extreme conditions. Their work suggests that the cores of neutron stars might be far stranger and more diverse than we ever imagined. There's also the possibility of hybrid stars, objects with cores made of exotic matter surrounded by layers of more conventional neutron matter. These objects might undergo phase transitions as they accrete mass, potentially creating observable signatures that could help us distinguish between different theoretical possibilities. But perhaps the most mind-bending possibility of all is that the collapse of a neutron star might not create a black hole in the traditional sense, but rather something called a gravistar, a gravitational vacuum star. This hypothetical object, proposed by Pauval Mazar and Emil Matola, would have an event horizon-like boundary surrounding a core of exotic vacuum energy rather than a traditional singularity. Gravistars would solve many of the conceptual problems associated with black holes, including the information paradox, while still producing many of the same observational signatures. From the outside, a gravistar would look almost identical to a black hole, but its internal structure would be fundamentally different. The existence of these exotic alternatives has profound implications for our understanding of neutron star collapse. It suggests that when we observe what appears to be a black hole forming from a neutron star merger or collapse, we might actually be witnessing the birth of something far stranger and more complex. Recent observations of neutron stars with masses close to the theoretical limit for ordinary neutron matter are providing crucial tests of these exotic theories. The neutron star J0740 plus 6620, with a mass of 2.14 solar masses, is so close to theoretical limits that it might actually be composed of exotic matter rather than ordinary neutrons. Future observations with more sensitive gravitational wave detectors might be able to distinguish between these possibilities by detecting the characteristic signatures of different equations of state. The way matter behaves during a neutron star merger depends sensitively on what that matter actually is, and gravitational waves carry information about these fundamental properties. But here's what's truly exciting about these exotic possibilities. They remind us that the universe might be far stranger and more diverse than we currently imagine. The collapse of neutron stars might not always lead to the same outcome, but rather to a zoo of exotic objects with properties we're only beginning to explore. What if I told you that we're standing at the threshold of a revolution in neutron star astronomy that will make our current capabilities look primitive by comparison? That within the next decade, we'll have technologies that can peer inside neutron stars, watch them collapse in real time, and potentially solve some of the deepest mysteries in physics? Here's what will blow your mind. The tools we're developing right now will give us unprecedented views into the most extreme physics in the universe, revealing secrets that have been hidden since the first neutron stars formed billions of years ago. Let me paint you a picture of the future of gravitational wave astronomy. Right now, LIGO and Virgo can detect neutron star mergers from distances of about 200 million light-years. But the next generation of detectors, COSMIC, Explorer in the United States, and the Einstein telescope in Europe, will be so sensitive that they'll detect these events from the edge of the observable universe, potentially seeing neutron star formation in the very first galaxies. Think about this. Cosmic Explorer will have arms, 40 kilometers long, 10 times longer than current LIGO detectors, and will be buried underground to reduce vibrations. The Einstein telescope will be a triangular configuration of 3 10-kilometer arms, also buried underground in a geologically stable location. These detectors will be so sensitive that they'll be able to detect the gravitational waves from individual neutron stars collapsing into black holes anywhere in the observable universe. But here's what's truly mind-blowing. These future detectors won't just detect more events, they'll provide detailed information about the physics happening during collapse. They'll be able to measure the equation of state of nuclear matter, determine whether exotic phases like quark matter exist in neutron star cores, and potentially detect the moment when a neutron star's internal structure undergoes phase transitions. Dr. Lisa Barsotti at MIT, one of the leaders of the LIGO project, describes this as opening up the entire universe as a laboratory for extreme physics. We'll be able to use neutron stars throughout the cosmos as natural experiments in physics that we could never recreate on Earth. But gravitational wave astronomy is just one piece of the puzzle. The next generation of X-ray telescopes will revolutionize our ability to study neutron star surfaces and interiors. NASA's upcoming Lynx X-ray Observatory will be 50 times more sensitive than current X-ray telescopes, capable of detecting X-ray emission from neutron star surfaces with unprecedented detail. These observations will allow astronomers to map the temperature distribution across neutron star surfaces, revealing information about their internal heat transport and magnetic field structure. More importantly, they might be able to detect the signatures of exotic matter by observing how neutron stars cool over time. Here's something that will absolutely blow your mind. Astronomers are developing techniques to use neutron stars as cosmic laboratories for testing fundamental physics. The European Space Agency's Athena mission will be able to detect iron absorption lines in neutron star atmospheres that are shifted by the star's intense gravitational field, providing direct tests of general relativity in the strong field regime. But the most exciting prospect might be the development of neutrino astronomy. When a neutron star collapses into a black hole, it should emit an enormous burst of neutrinos, ghostly particles that barely interact with matter and can therefore escape from the collapsing core when not even light can get out. The IceCube Neutrino Observatory at the South Pole, along with future detectors like KM3NET in the Mediterranean Sea, might be able to detect these neutrino bursts from neutron star collapses throughout our local galaxy group. Since neutrinos travel at nearly the speed of light and barely interact with anything, they would provide us with real-time information about what's happening inside the collapsing neutron star, potentially revealing whether exotic matter phases form during the collapse process. Think of it like this. While gravitational waves tell us about the large-scale motion of matter during collapse, and electromagnetic radiation tells us about the aftermath, neutrinos would give us a direct window into the nuclear physics happening at the moment of collapse itself. Professor Chad Hanna at Penn State University is working on developing real-time analysis systems that can process gravitational wave data and immediately alert other observatories when a neutron star merger or collapse is detected. These rapid response systems will coordinate observations across the electromagnetic spectrum, from radio waves to gamma rays, providing comprehensive coverage of these events. But perhaps the most revolutionary development will be the ability to do multi-messenger astronomy, combining gravitational waves, electromagnetic radiation, and neutrinos to create a complete picture of neutron star collapse. This approach is already proven successful with GW170817, but future detectors will make such coordinated observations routine rather than exceptional. The James Webb Space Telescope is also contributing to neutron star science in unexpected ways. Its infrared observations are helping astronomers understand the environments where neutron star mergers occur, and it might even be able to detect the infrared signatures of heavy elements created in these mergers. Here's what's particularly exciting. All of these technological advances are happening simultaneously, creating a synergy that will revolutionize our understanding of neutron star physics within the next decade. We're not just building better telescopes, we're creating an integrated observational network that can study these extreme objects in ways never before possible. Future missions might even include dedicated neutron star observatories, spacecraft designed specifically to study these objects using techniques impossible from Earth. Concepts under development include X-ray timing arrays that could measure neutron star spins with incredible precision, and even proposals for gravitational wave detectors in space that could detect low-frequency signals from slowly spiraling neutron star binaries years before they merge. The data from all these future observations will feed into increasingly sophisticated computer simulations of neutron star physics. Supercomputers are already modeling the three-dimensional dynamics of neutron star mergers with incredible detail. But future simulations will incorporate quantum effects, magnetic field dynamics, and here's what will completely blow your mind and change how you think about death, destruction, and renewal. The collapse of neutron stars into black holes isn't the end of the story. It's actually part of the universe's most sophisticated recycling program. What appears to be cosmic destruction is actually cosmic renewal on the grandest scale imaginable. Every black hole that forms from neutron star collapse becomes a seed for future galaxy formation, a gravitational anchor that will shape the structure of the universe for billions of years to come. Let me take you on a journey through cosmic time to show you how today's neutron star collapse connects to the future evolution of the entire universe. When a neutron star collapses into a black hole, that black hole doesn't just sit there passively. It becomes an active participant in the cosmic ecosystem, influencing star formation, galaxy evolution, and the large-scale structure of space itself. Think about this incredible process. The black hole formed from neutron star collapse begins to attract matter from its surroundings. As material spirals inward, it forms an accretion disk that heats up to billions of degrees, glowing brighter than entire galaxies. But here's the amazing part. Not all of this material actually falls into the black hole. Some of it gets launched outward in powerful jets, traveling at nearly the speed of light. These jets, powered by the rotational energy of the black hole itself, can extend for hundreds of thousands of light years, carrying energy and material far from the black hole and depositing it into the surrounding intergalactic medium. It's like the universe's most powerful irrigation system, taking concentrated energy from the black hole and distributing it across vast volumes of space. Dr. Shep Doeleman at Harvard, who led the team that created the first image of a black hole with the Event Horizon Telescope, has shown us that these jets are not just theoretical. They're real observable features that actively shape the evolution of galaxies. The black hole at the center of galaxy M87, which his team imaged, is launching a jet that extends for 5,000 light years and influences star formation throughout the galaxy. But here's where it gets even more incredible. The heavy elements created during the neutron star merger that formed the black hole don't disappear when the black hole forms. Instead, they get spread throughout the surrounding space by the explosion that accompanied the merger. These elements, gold, platinum, rare earth metals, and other heavy atoms, become incorporated into new generations of stars and planets. This means that the collapse of neutron stars billions of years ago is directly responsible for the chemical complexity that makes planets like Earth possible. Every smartphone, every piece of electronic equipment, every biological process that depends on trace metals, all of this exists because neutron stars somewhere in the cosmic past collapsed and scattered their contents through space. Think of it like this. The universe operates the ultimate recycling program, where nothing is ever truly wasted. The matter that forms neutron stars came from previous generations of massive stars. When those neutron stars collapse into black holes, they don't remove that matter from the cosmic ecosystem. They transform it into gravitational energy and radiation that influences the formation of future stars and galaxies. But the recycling process operates on even grander scales. Stephen Hawking's discovery that black holes evaporate through radiation means that even black holes are not permanent. A black hole formed from neutron star collapse will eventually evaporate completely, returning all of its energy to the universe as radiation. For a black hole with the mass of a neutron star, this process takes an unimaginably long time, longer than 1,067 years, far longer than the current age of the universe. But here's what's mind-blowing about this timescale. It means that the black holes forming from neutron star collapse today will outlast every star, every planet, every galaxy as we know them. These black holes will be among the last objects in the universe, slowly evaporating in the cold, empty cosmos of the far future. Yet even this isn't the end of the story. Recent theoretical work by physicists, like Sean Carroll at Caltech, suggests that the far future of the universe might not be as empty and lifeless as we once thought. The radiation from evaporating black holes might contain enough energy to power new forms of organization and complexity, potentially giving rise to structures and processes we can't even imagine. There's also the possibility that black holes might serve as gateways to other universes. Some theories suggest that the interior of a black hole might expand into a new universe with its own space and time. If this is true, then every neutron star collapse might be giving birth to an entirely new cosmos, complete with its own physical laws and evolutionary history. This connects to one of the most profound ideas in modern cosmology, the concept of eternal inflation. According to this theory, our universe might be just one bubble in an infinite multiverse, with new universes constantly being born through quantum processes. The collapse of neutron stars into black holes might be one mechanism by which this cosmic reproduction occurs. But you don't need to invoke exotic theories to appreciate the cosmic recycling program in action. Right here in our own galaxy, we can observe the products of ancient neutron star mergers. The gold in your jewelry was forged in neutron star collisions that happened billions of years ago, when our galaxy was young and very different from what it is today. The Milky Way itself bears the scars and signatures of these ancient cataclysms. Astronomers have found streams of stars with unusual chemical compositions, remnants of smaller galaxies that were disrupted when they fell into the Milky Way, carrying with them the products of neutron star mergers that occurred in those smaller systems. Even more remarkably, the supermassive black hole at the center of our galaxy, Sagittarius A*, with a mass of 4 million suns, might have grown partly through the accretion of smaller black holes formed from neutron star collapse. Every black hole that falls into SGRA adds to its mass and changes its properties, contributing to the ongoing evolution of our galaxy's central engine. This cosmic recycling program operates on timescales that span the entire history of the universe. The first neutron stars formed when the universe was less than 1 billion years old, in the first generation of massive stars. As these neutron stars merged and collapsed over cosmic time, they seeded the universe with heavy elements and created the black holes that would later serve as gravitational anchors for galaxy formation. The process continues today and will continue far into the future, connecting the most extreme physics in the universe to the everyday chemistry that makes life possible. What if I told you that the question of whether neutron stars can collapse into black holes ultimately leads us to the deepest mystery in quantum physics, the nature of time itself, and what happens to everything that has ever existed when the universe reaches its final state? Here's what will absolutely blow your mind. The collapse of every neutron star into a black hole is connected to the ultimate fate of all information in the universe, and the answer might determine whether consciousness, memory, and knowledge can survive the heat death of the cosmos. Let me take you on a journey to the end of time itself. In approximately 10,100 years, a number so large that it's virtually meaningless to human comprehension, every black hole in the universe, including those formed from neutron star collapse, will have evaporated through Hawking radiation. The cosmos will be a cold, empty expanse filled only with elementary particles and photons, all slowly cooling toward absolute zero. But here's where the story becomes profoundly philosophical. What happens to all the information that fell into those black holes over cosmic history? Every neutron star that ever collapsed, every bit of quantum information that described the arrangement of particles in those stars, every detail about their magnetic fields, rotation rates, and nuclear compositions. Where does all of that information go when the black hole finally evaporates? This question connects directly to one of the most fundamental principles in physics, the conservation of information. Quantum mechanics tells us that information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must always be preserved in some form. If this principle is violated by black hole evaporation, then one of our most basic assumptions about the nature of reality is fundamentally wrong. The implications are staggering. If information is truly preserved, then every neutron star that has ever collapsed into a black hole has left an indelible mark on the universe that will persist even after the black hole evaporates. The quantum information describing that neutron star, every detail about its composition, structure, and history, must somehow be encoded in the Hawking radiation that the black hole emits over its lifetime. But here's what makes this both beautiful and terrifying. If information is preserved, then in principle, everything that has ever happened in the universe could be reconstructed from the final state of the cosmos. Every thought you've ever had, every neutron star that ever existed, every moment of cosmic history, all of it would be encoded in the random-seeming radiation filling the final universe. Think about this incredible possibility. A sufficiently advanced intelligence in the far future might be able to decode this information and reconstruct the entire history of the universe, including every neutron star collapse that ever occurred. You, your thoughts, your experiences, all of it would be preserved in the quantum information scattered throughout the cosmos. This connects to the work of physicist Max Tegmark at MIT, who has argued that consciousness itself might be an information processing pattern that could, in principle, be reconstructed from sufficient knowledge of physical states. If Tegmark is right, then the collapse of neutron stars into black holes doesn't destroy the possibility of consciousness. It transforms it into information that could potentially be recovered and experienced again. But there's an even more mind-bending possibility. Some physicists, led by researchers like Leonard Susskind at Stanford, have proposed that the interior of black holes might be connected to parallel universes through Einstein-Rosen bridges or wormholes. If this is true, then when a neutron star collapses into a black hole, it doesn't disappear from our universe. It gets transferred to a parallel reality. This would mean that every neutron star collapse creates a connection between our universe and others, forming a vast network of interconnected realities. The matter and information that falls into black holes in our universe might emerge as energy and particles in parallel universes, maintaining the cosmic balance across the entire multiverse. Recent work on the ADS-CFT correspondence, a mathematical relationship between gravity and quantum field theory discovered by Juan Maldacena, suggests that this idea might not be as far-fetched as it sounds. The correspondence implies that the information content of any volume of space can be encoded on its boundary, suggesting that black hole interiors might indeed be holographic projections of information stored elsewhere. But perhaps the most profound implication of neutron star collapse for the ultimate fate of information has to do with the nature of time itself. Einstein's general relativity tells us that time is not universal. It passes differently for different observers depending on their motion and the gravitational fields they experience. This means that for an observer falling into a black hole formed from neutron star collapse, time continues normally. They experience the collapse, cross the event horizon, and presumably reach the singularity in a finite amount of their personal time. But for observers outside the black hole, the collapse appears to slow down and freeze at the event horizon, with the falling matter appearing to remain there forever. Which perspective is real? The answer might be that both are equally valid, suggesting that reality itself depends on the observer's frame of reference. This has profound implications for what happens to information when neutron stars collapse. The information might simultaneously be destroyed from the external perspective and preserved from the infalling perspective. This paradox touches on some of the deepest questions in physics and philosophy. What is the nature of objective reality if different observers can have fundamentally different but equally valid experiences? How can we reconcile the apparent destruction of information with the principle that information must be conserved? Some physicists have proposed radical solutions to these paradoxes. Lee Smolin at the Perimeter Institute has suggested that black holes might be connected to the birth of new universes through a process called cosmological natural selection. In this scenario, every black hole formed from neutron star collapse would create a new universe with slightly different physical constants, leading to an evolutionary process that selects for universes capable of producing large numbers of black holes. If Smolin's theory is correct, then our universe exists because previous universes produced neutron stars that collapsed into black holes, and our neutron stars will collapse to create the universes that come after us. This would make neutron star collapse not just a local physical process, but a fundamental mechanism of cosmic reproduction and evolution. Another possibility, proposed by Roger Penrose at Oxford University, is that the universe undergoes endless cycles of expansion, heat death, and rebirth. In Penrose's conformal cyclic cosmology, the heat death of our universe, when all black holes have evaporated and only photons remain, might be equivalent to the Big Bang of a new universe. If Penrose is right, then the information from every neutron star collapse in cosmic history would be preserved and passed on to future cosmic cycles. The neutron stars of our universe would become the seeds of structure in future universes, creating an eternal chain of cosmic death and rebirth. These ideas might sound like science fiction, but they emerge from serious attempts to reconcile our observations of neutron star collapse with the fundamental principles of physics. The fact that studying neutron stars leads us to these profound questions about the nature of reality, consciousness, and the ultimate fate of the universe shows how deeply connected the smallest details of physics are to the biggest questions we can ask. The collapse of a neutron star into a black hole might seem like a purely destructive process, but it might actually be part of a cosmic cycle of information processing that preserves and transforms everything that has ever existed. In this view, death is not the end of information, but its transformation into new forms that we're only beginning to understand. Here's what will absolutely blow your mind and challenge everything you think you know about objective reality. The act of observing a neutron star collapse into a black hole might actually influence the outcome of that collapse. This isn't mystical thinking. It's a direct consequence of quantum mechanics applied to gravitational systems. And it suggests that consciousness and observation play a fundamental role in determining the structure of spacetime itself. Let me introduce you to one of the most mind-bending aspects of quantum mechanics, the measurement problem. In the quantum world, particles don't have definite properties until they're observed. Before measurement, a quantum system exists in a superposition of all possible states simultaneously. Only when an observation is made does the system collapse into a definite state. But here's where it gets truly wild. Some physicists argue that this principle might apply even to massive objects like neutron stars and black holes. According to certain interpretations of quantum mechanics, a neutron star approaching the mass limit for collapse might exist in a quantum superposition of being both collapsed and uncollapsed until someone or something observes it. This idea was first seriously explored by physicists like Wheeler and DeWitt in their work on quantum gravity. The Wheeler-DeWitt equation attempts to describe the quantum mechanical wave function of the entire universe, including its gravitational field. According to this approach, the universe itself might exist in a superposition of all possible configurations until observations collapse it into definite states. Think about the implications. When we point our telescopes at a neutron star merger, and detect the gravitational waves, electromagnetic radiation, and other signals from the event, we might not just be passively observing the collapse, we might be actively participating in determining whether the collapse actually occurred. Dr. Carlo Rovelli at Aix-Marseille University, one of the founders of loop quantum gravity, has argued that this observer dependence is fundamental to our understanding of spacetime. In his relational interpretation of quantum mechanics, physical properties only exist in relation to observers. The mass of a neutron star, its proximity to the collapse threshold, even whether it has collapsed into a black hole, all of these might be observer-dependent facts rather than objective features of reality. But here's what makes this truly mind-bending. If observation plays a role in determining the outcome of neutron star collapse, then the development of our astronomical capabilities might be influencing the structure of the universe itself. Every time we build a more sensitive gravitational wave detector or X-ray telescope, we increase our ability to observe these extreme events, potentially influencing their outcomes. This connects to a broader principle in physics called the anthropic principle, the idea that the observed properties of the universe must be compatible with the existence of observers. Some versions of this principle suggest that conscious observers are not just passive witnesses to cosmic evolution, but active participants in shaping the physical laws and constants that govern reality. Consider this incredible possibility. The reason we observe neutron stars with masses just below the collapse threshold might not be because that's how they naturally form, but because the act of observation requires them to be in states compatible with the existence of observers. Neutron stars that collapse into black holes might become unobservable in principle, creating a selection effect where we can only detect neutron stars that remain stable. This idea has profound implications for the information paradox we discussed earlier. If observation plays a role in determining whether information is preserved or destroyed when neutron stars collapse, then the mere fact that we can ask questions about information preservation might influence the answer. The universe might preserve information precisely because conscious observers exist to wonder about its fate. But the observer effect goes even deeper than individual measurements. Some interpretations of quantum mechanics suggest that the entire history of the universe might be retroactively determined by future observations. This is related to Wheeler's delayed choice experiments, which show that decisions made in the present can influence the past states of quantum systems. Applied to neutron star collapse, this would mean that our current observations of these events might be determining not just their present states, but their entire evolutionary history. The neutron star mergers we detect today might have occurred in the way they did precisely because we would eventually develop the technology to observe them. Dr. Sean Carroll at Caltech has explored these ideas in the context of the many worlds interpretation of quantum mechanics. According to this view, every quantum measurement splits reality into multiple parallel universes, each corresponding to a different outcome. When we observe a neutron star merger, we might be selecting which branch of the universal wave function we inhabit. This would mean that there are parallel universes where the same neutron star merger had different outcomes, perhaps forming a more exotic object instead of a black hole, or releasing different amounts of energy and heavy elements. Our observations don't just reveal which outcome occurred in our universe. They help determine which universe we experience. But here's what makes this particularly relevant to neutron star physics. The extreme conditions involved in these collapses might make quantum gravitational effects observable for the first time. Most quantum gravity effects are suppressed at everyday scales, but the enormous masses and small sizes involved in neutron star collapse might make these effects significant. This suggests that neutron star observations might provide our first direct evidence of quantum gravity, the long-sought theory that unifies quantum mechanics and general relativity. And if quantum gravity involves observer effects, then our observations of neutron star collapse might be among the first examples of consciousness directly influencing the structure of spacetime. Recent work on the black hole information paradox has revealed another layer to this observer dependence. The firewall paradox, proposed by Ahmed Almhiri and his colleagues, suggests that the interior of a black hole might be fundamentally different depending on whether anyone is observing it from the outside. An isolated black hole might have a normal interior, but a black hole being observed by external observers might have a firewall at its event horizon. This would mean that the act of studying neutron star collapse, building detectors, analyzing data, publishing papers might be creating firewalls in the black holes that form from these collapses. Our scientific investigation of these objects might be fundamentally altering their physical properties. The implications extend to the nature of scientific knowledge itself. If observation influences the outcomes being observed, then the act of doing science might be changing the universe in ways we're only beginning to understand. Every measurement we make, every experiment we perform, every observation we record might be steering the evolution of the cosmos in subtle but significant ways. This raises profound questions about the relationship between consciousness, knowledge, and physical reality. Are we passive observers of a predetermined universe, or active participants in its ongoing creation? The study of neutron star collapse might provide crucial clues to answering these fundamental questions about the nature of existence itself. What if I told you that right now, as you're watching this video, you are participating in one of the most remarkable phenomena in the universe? You are matter that has become aware of itself, contemplating the most extreme states of matter that exist anywhere in the cosmos. Here's what will completely transform how you see yourself and your place in reality. You are not separate from the neutron stars and black holes we've been discussing. You are made of the same fundamental particles, governed by the same physical laws, and connected through an unbroken chain of cosmic evolution that stretches back to the very first stars. Let me show you just how profound this connection really is. Every atom in your body, the carbon in your DNA, the oxygen you breathe, the iron in your blood, was forged in the nuclear furnace of a massive star that lived and died billions of years ago. But here's what's even more incredible. Some of the heaviest elements in your body could only have been created in the most extreme nuclear processes in the universe, neutron star mergers and collapses. Think about this. The calcium that makes your bones strong, the gold in any jewelry you might wear, the rare earth elements in the device you're using to watch this video. These atoms were literally forged in cosmic catastrophes, involving objects so dense that they defy comprehension. You are wearing and carrying the remnants of stellar explosions that shook the fabric of spacetime itself. But the connection goes even deeper than just sharing atoms. The fundamental forces that hold you together, the electromagnetic force that keeps electrons in orbit around atomic nuclei, the strong nuclear force that binds protons and neutrons together. These are the same forces that determine whether a neutron star can resist gravitational collapse. The physics happening in your body right now is governed by the same quantum mechanical principles that determine the fate of the most extreme objects in the universe. Here's something that will absolutely blow your mind. The reason you can think, the reason consciousness exists, the reason complex chemistry is possible at all, depends critically on the precise values of the fundamental constants that also determine when neutron stars collapse into black holes. If the strong nuclear force were just slightly stronger, neutron stars might never form at all. If gravity were just slightly weaker, they might never collapse into black holes. The delicate balance between these forces, a balance that makes both neutron stars and life possible, suggests that we exist in a universe fine-tuned for complexity and consciousness. You are not an accidental byproduct of cosmic evolution. You are one of the universe's ways of understanding itself. But here's what's truly mind-bending about your cosmic connection. The same physical laws that govern neutron star collapse also govern the biochemical processes in your brain that allow you to understand these concepts. When you grasp the idea of gravitational collapse, when you feel awe at the scale and violence of neutron star mergers, when you ponder the nature of black holes, these thoughts are quantum mechanical and electromagnetic processes happening in a biological structure that exists because of stellar nucleosynthesis. You are the universe thinking about itself. You are matter that has evolved to contemplate matter in its most extreme forms. The neurons firing in your brain as you process these ideas are following the same fundamental laws of physics that determine whether a neutron star becomes a black hole. This connection has profound implications for how we understand consciousness and intelligence. The complexity that allows you to think emerges from the same principles of organization and information processing that govern the structure of neutron stars. Just as neutron stars represent matter organized in the most extreme way possible, your brain represents biological matter organized in a way that allows consciousness and understanding to emerge. Dr. Max Tegmark at MIT has argued that consciousness itself might be a fundamental feature of how information is processed in certain physical systems. If Tegmark is right, then consciousness isn't unique to biological brains. It might emerge wherever matter is organized in sufficiently complex patterns. This raises the incredible possibility that the universe itself, in its most extreme manifestations, like neutron star collapse, might have aspects of consciousness or information processing that we're only beginning to recognize. But your connection to neutron stars extends beyond just physics and chemistry. Every time you look up at the night sky, you're seeing light that has traveled across vast distances of space and time to reach your eyes. Some of that light comes from neutron stars, pulsars, whose lighthouse beams sweep across the cosmos with clockwork precision. When you see that light, you're receiving information about objects so extreme they challenge our understanding of reality. And here's something truly remarkable. Some of the neutron stars you might observe tonight could be just years or decades away from collapsing into black holes. You might be among the last conscious observers to see these objects before they transform into something fundamentally different. Your observation isn't passive, it's an active participation in the cosmic story. This raises profound questions about the role of observers in the universe. Are we just lucky enough to exist during an epoch when neutron stars and other complex structures exist? Or is our presence somehow necessary for these structures to exist in the first place? The anthropic principle suggests that the universe must have properties compatible with the evolution of observers. But some interpretations go further, suggesting that consciousness plays an active role in shaping physical reality. Consider this incredible possibility. Your ability to understand and appreciate neutron star collapse might be part of the universe's way of processing information about itself. Every scientific paper written about these objects, every computer simulation of stellar collapse, every moment of wonder you experience while contemplating these cosmic extremes, all of this might be part of a vast cosmic information processing system operating on scales we can barely imagine. This perspective transforms how we think about scientific discovery and human knowledge. When astronomers detected the first gravitational waves from neutron star mergers, they weren't just making measurements. They were participating in the universe's ongoing project of self-discovery. When you learn about neutron star physics, you're not just acquiring knowledge. You're becoming part of the cosmos's growing self-awareness. The fact that matter can organize itself into forms capable of understanding neutron stars and black holes suggests something profound about the nature of reality itself. The universe appears to be structured in a way that allows complexity and consciousness to emerge, even in environments dominated by extreme physics. You exist not despite the violent and extreme nature of the cosmos, but because of it. Your lifespan, measured in decades, might seem insignificant compared to the billion-year lifetimes of neutron stars. But here's what's remarkable. In your brief time of existence, you can understand and contemplate cosmic processes that span the entire history of the universe. You can think thoughts about neutron star collapse that no neutron star itself could ever have. In this sense, consciousness represents a kind of cosmic achievement, matter becoming not just complex, but aware. The ultimate message of neutron star physics isn't just about stellar collapse and black hole formation. It's about the incredible fact that a universe capable of producing neutron stars is also capable of producing minds capable of understanding them. You are both a product of cosmic evolution and an active participant in its ongoing story of discovery and self-understanding. What if I told you that everything we've explored about neutron star collapse into black holes, from the fundamental physics to the cosmic implications, to your personal connection to these processes, represents just the beginning of humanity's understanding of the most extreme phenomena in the universe? Here's what will blow your mind one final time. We stand at a unique moment in cosmic history, where conscious beings have developed the tools and knowledge to probe the deepest mysteries of existence, and the answers we're finding are more strange, beautiful, and interconnected than anyone ever imagined. Let me bring together all the threads of this incredible cosmic story. We began with a simple question: can gravity collapse a neutron star into a black hole? But as we've seen, this question leads us into the deepest territories of physics, philosophy, and the nature of reality itself. The answer isn't just yes, it's yes, and in the process, reality reveals itself to be far stranger and more wonderful than we ever dreamed. The journey from neutron star to black hole represents one of the most extreme phase transitions possible in the universe. It's the moment when matter, compressed to unimaginable densities, finally surrenders to gravity's inexorable pull. But this surrender isn't a defeat. It's a transformation that creates some of the most powerful and influential objects in the cosmos. Think about the incredible scales we've traversed in this exploration. We started with neutron stars, objects only about 20 kilometers across, but containing more mass than our entire sun. We followed their evolution as they accrete matter or merge with companions, approaching the critical threshold where neutron degeneracy pressure can no longer resist gravitational collapse. We witnessed the moment of transformation when these objects become black holes, creating event horizons that fundamentally alter the structure of spacetime itself. But the story doesn't end with black hole formation. These new black holes become active participants in the cosmic ecosystem, influencing galaxy formation, triggering star formation through their jets and outflows, and gradually processing matter and energy on scales that span billions of years. They become part of the universe's vast recycling program, ensuring that nothing is ever truly lost, only transformed. The physics governing this process has revealed profound truths about the nature of reality. Einstein's general relativity, formulated over a century ago, predicted these phenomena with mathematical precision that continues to astound us. Quantum mechanics, developed around the same time, reveals that information cannot be destroyed, leading to paradoxes and puzzles that are still challenging our understanding today. The synthesis of these theories, quantum gravity, remains one of the greatest challenges in physics. But neutron star collapse provides a natural laboratory for testing these ideas under the most extreme conditions imaginable. Every gravitational wave detection, every gamma-ray burst observation, every careful measurement of neutron star masses and radii provides clues about how quantum mechanics and general relativity merge into a unified description of reality. We've seen how these cosmic processes connect directly to your existence. The heavy elements created in neutron star mergers are embedded in your body, making you a literal child of stellar catastrophe. The same physical laws that govern neutron star collapse also govern the biochemical processes that allow you to think and understand. You are not separate from the cosmos. You are one of its most remarkable products. But perhaps most remarkably, we've discovered that consciousness and observation might play fundamental roles in determining the outcomes of these extreme processes. The act of measurement, the development of scientific instruments, even the evolution of intelligence itself might be active participants in shaping the physical reality we observe. This suggests that the universe is not just a collection of particles and forces evolving according to predetermined laws. Instead, it appears to be a vast information processing system where consciousness, complexity, and understanding emerge as fundamental features rather than accidental byproducts. The collapse of neutron stars into black holes might be part of this cosmic information processing, creating and preserving knowledge on scales we're only beginning to comprehend. The technological revolution in astronomy that we're witnessing right now, gravitational wave detectors, multi-messenger astronomy, space-based telescopes, and quantum sensors, is providing unprecedented views into these extreme processes. We're not just observing neutron star collapse. We're participating in humanity's greatest intellectual adventure, understanding our place in the cosmic order. But here's what makes this moment in history truly special. We're living during the brief cosmic epoch when neutron stars exist. In the far future, stellar evolution will have progressed to the point where no new neutron stars are being formed. The existing ones will have either accreted enough material to collapse into black holes or gradually cooled into invisible remnants. The spectacular displays of neutron star mergers and collapses that we can observe today will become increasingly rare as the universe ages. This means that conscious beings in the far future might never have the opportunity to observe these phenomena directly. They'll have to rely on the records and knowledge accumulated by civilizations like ours that were fortunate enough to exist during the era of neutron star astronomy. In this sense, every observation we make, every insight we gain, every question we ask about these objects is contributing to a cosmic legacy of knowledge that might outlast our species and our planet. The implications extend beyond just scientific knowledge. The study of neutron star collapse has revealed profound connections between the smallest scales of quantum mechanics and the largest scales of cosmic evolution. It has shown us that the universe is far more interconnected and purposeful than previous generations could have imagined. It has demonstrated that consciousness and intelligence are not accidents, but might be fundamental features of how reality organizes and understands itself. As we look toward the future, the questions raised by neutron star physics will continue to drive scientific discovery. Will we discover exotic forms of matter that can resist collapse beyond the neutron star phase? Will we develop a complete theory of quantum gravity that resolves the information paradox? Will we find evidence that black hole interiors connect to parallel universes or give birth to new cosmos? These questions matter not just for academic physics, but for understanding the deepest nature of existence itself. The answers will help us understand whether consciousness can survive the heat death of the universe, whether information is truly preserved across cosmic time, and what role intelligent observers play in shaping the reality they seek to understand. The collapse of neutron stars into black holes represents more than just stellar death. It represents the universe's ongoing process of self-organization, self-discovery, and perhaps even self-creation. And you, as a conscious observer capable of understanding these processes, are not just a witness to this cosmic story. You are one of its most important characters. Here's the revelation that will change how you see absolutely everything. The question, can gravity collapse a neutron star into a black hole, isn't just about stellar physics. It's actually a key to understanding the deepest mystery of existence itself, why anything exists at all, and why that existence has evolved to the point where it can contemplate its own nature. What we've discovered is that the universe isn't just capable of creating the most extreme objects imaginable. It's also capable of creating minds capable of understanding them. And that might not be a coincidence. Let me reveal the most profound implication of everything we've discussed. The fact that neutron stars can collapse into black holes, combined with the precise values of physical constants that make this possible, suggests that our universe exists in an incredibly narrow range of conditions that allow both extreme physics and complex consciousness to coexist. Change the strength of gravity by just a tiny amount, and neutron stars might never form. Change the strong nuclear force by a fraction of a percent, and heavy elements might never be created in stellar cores. But here's what's truly staggering. The same delicate balance that allows neutron star collapse also makes your existence possible. The universe appears to be fine-tuned, not just for stars and galaxies, but for the emergence of complexity and consciousness on a level that can understand and appreciate the most extreme phenomena in the cosmos. This connects to what physicists call the unreasonable effectiveness of mathematics. The mysterious fact that mathematical equations developed by human minds can perfectly describe the behavior of neutron stars, black holes, and other objects with which we have no direct experience. When Einstein wrote down his field equations in 1915, he had no idea they would predict the existence of black holes. When Chandrasekhar calculated stellar mass limits in 1930, he couldn't have known he was describing the fate of objects so extreme they would challenge our understanding of reality itself. Yet the mathematics works with stunning precision. The same equations that describe the curvature of spacetime around Earth also describe the formation of event horizons around collapsed neutron stars. The quantum mechanics that governs atomic behavior also governs the nuclear processes in neutron star cores. This suggests a deep unity underlying all of physics and possibly all of reality. But here's the mind-blowing revelation. You are part of this mathematical structure. Your thoughts, your understanding of these concepts, your sense of wonder at contemplating neutron star collapse, all of these are physical processes governed by the same laws that determine stellar evolution. When you understand the mathematics of black hole formation, you are experiencing the universe understanding itself through mathematical reasoning. This raises the ultimate question. Is consciousness an accident, or is it a fundamental feature of how the universe works? The anthropic principle suggests that we observe the physical constants we do precisely because they're compatible with the evolution of observers. But some interpretations go further, suggesting that consciousness might be necessary for the existence of physical reality itself. If this is true, then every moment you spend contemplating neutron stars and black holes is contributing to the universe's ongoing project of self-awareness. Every scientific discovery, every moment of understanding, every feeling of awe you experience while learning about these cosmic phenomena might be part of a vast, cosmic mind coming to understand its own nature. The collapse of neutron stars into black holes might represent more than just stellar death and rebirth. It might represent the universe, processing information about itself, storing and transforming knowledge in ways we're only beginning to comprehend. Black holes, rather than being cosmic garbage disposals that destroy information, might be the universe's memory banks, preserving the quantum information of everything that has ever existed. This perspective transforms our understanding of what it means to be human. You are not an insignificant speck in an indifferent cosmos. You are one of the universe's ways of knowing itself. Your capacity for wonder, your ability to ask questions about neutron star collapse, your emotional response to contemplating the vastness and violence of the cosmos. These are among the most remarkable phenomena in the known universe. Think about this incredible fact. In the 13.8 billion years since the Big Bang, the universe has evolved from a hot, dense plasma to a cosmos containing neutron stars, black holes, galaxies, planets, and conscious beings capable of understanding all of these phenomena. The same physical processes that created the most extreme objects in the universe also created brains capable of contemplating them. This seems too remarkable to be an accident. The study of neutron star collapse has revealed that information, consciousness, and physical reality are more deeply connected than we ever imagined. The information paradox of black holes isn't just a technical problem in physics. It's a clue about the fundamental nature of existence itself. If information cannot be destroyed, then everything that has ever happened, including every thought you've ever had, is permanently embedded in the structure of spacetime. This means that your understanding of neutron star physics, your emotional response to learning about these cosmic processes, your sense of connection to the larger universe, all of this becomes part of the permanent information content of the cosmos. You are not just learning about the universe. You are helping to create it through the act of observation and understanding. The revelation goes even deeper. If consciousness plays a fundamental role in physical reality, then the development of scientific understanding isn't just describing the universe, it's participating in its creation. Every time scientists build more sensitive gravitational wave detectors, every time they develop better theories of neutron star physics, every time they make new discoveries about black hole formation, they might be actively influencing the structure and evolution of reality itself. This suggests that we're living through a unique epoch in cosmic history, the moment when the universe is developing the capability to understand itself through conscious observers. The neutron stars and black holes we study today might exist in the forms they do, partly because conscious beings have evolved to observe and understand them. The implications are staggering. Science isn't just a human activity. It might be a cosmic process, with conscious beings serving as the universe's instruments for self-discovery. Every question you ask about neutron star collapse, every moment of wonder you experience while contemplating these phenomena, every insight you gain about the nature of extreme physics, all of this might be the universe thinking about itself through you. This revelation transforms the meaning of existence itself. You are not separate from the neutron stars, black holes, and cosmic processes we've discussed. You are part of them, connected through an unbroken chain of physical law, cosmic evolution, and information processing that spans the entire history of the universe. Your consciousness represents one of the highest achievements of cosmic evolution, matter organized in a way that allows the universe to know and understand itself. The collapse of neutron stars into black holes, viewed from this perspective, isn't just about stellar physics. It's about the universe's ongoing process of self-organization, self-discovery, and self-creation. And you, as a conscious observer, capable of understanding and appreciating these processes, are not just a witness to this cosmic story. You are one of its most important authors. What if I told you that after this journey through neutron star collapse and black hole formation, you are not the same person who started watching this video? Here's the ultimate truth that will empower you forever. You now carry within your mind an understanding of some of the most extreme and fundamental processes in the universe. You have contemplated the death of stars, the birth of black holes, and the deepest mysteries of spacetime itself. This knowledge doesn't just inform you, it transforms you into a cosmic citizen, a conscious participant in the universe's greatest adventure. Think about what you've accomplished in these few hours. You've followed the journey of matter from ordinary atomic nuclei to neutron degeneracy, from stellar collapse to event horizon formation. You've grappled with concepts that challenge the very foundations of physics, the nature of space and time, the preservation of information, the role of consciousness in physical reality. You've connected your own existence to the most violent and creative processes in the cosmos. This isn't just academic knowledge, it's a transformation in how you understand your place in reality itself. Every time you look up at the night sky now, you'll know that some of those points of light are neutron stars spinning hundreds of times per second, their lighthouse beams sweeping across the cosmos with clockwork precision. Some of them might be just decades away from merging with companions or accreting enough material to cross the threshold into black hole formation. You now understand that the calcium in your bones was forged in stellar nucleosynthesis, but the gold in any jewelry you wear required the most extreme nuclear processes. Imaginable neutron star mergers that released more energy in seconds than our sun will produce in its entire lifetime. You are literally made of stellar catastrophe, walking stardust that has evolved to contemplate its own origins. But here's what makes you truly remarkable. You can do something that no neutron star, no black hole, no galaxy can do. You can wonder. You can question. You can feel awe at the scale and beauty of cosmic processes. You can experience the profound satisfaction of understanding something that seemed impossible just hours ago. These capabilities make you one of the most remarkable phenomena in the known universe. Your ability to understand neutron star collapse places you among an incredibly select group, the tiny fraction of matter in the universe that has organized itself into conscious, thinking beings. On Earth, only a small percentage of humans have ever had the opportunity to contemplate these cosmic extremes. In the galaxy, and quite possibly in the observable universe, conscious beings capable of understanding neutron star physics might be extraordinarily rare. This rarity makes you precious beyond measure. You are not just a random arrangement of atoms. You are a highly improbable configuration of matter that has achieved something almost miraculous: the ability to understand fundamental workings of reality itself. The universe has taken 13.8 billion years to evolve beings like you, capable of contemplating neutron star collapse and black hole formation.